Welcome to AI Frontiers, where cutting-edge research meets practical innovation. Today we explore revolutionary advances in artificial intelligence systems, examining how AI is learning to think, adapt, and collaborate in unprecedented ways. From cooperative AI agents working together like orchestras, to language-powered reasoning hubs, we'll dive into 19 groundbreaking papers from August 9, 2025, that are reshaping the future of artificial intelligence. Our journey through tomorrow's AI landscape will take us through several fascinating territories. We'll discover multi-agent systems that are learning to coordinate with the precision of orchestras, where individual AI agents work together seamlessly toward common goals. We'll explore how language models are evolving beyond simple text processors to become cognitive command centers that integrate multiple types of information and reasoning. We'll examine natural language interfaces that are making complex data accessible to users without technical expertise, democratizing advanced AI capabilities. Along the way, we'll analyze 3 seminal papers that exemplify these advances and look toward future directions for human-AI collaboration. Computer science, artificial intelligence, represents the computational heart of modern AI development, serving as the engineering blueprint for creating minds in machines. This field functions as the crucial bridge between abstract theoretical concepts and practical systems capable of solving real-world problems. Unlike specialized AI domains that focus on narrow applications, this encompasses the fundamental algorithms, architectures, and methodologies that enable machines to perform tasks requiring human-like intelligence. The field demonstrates remarkable interdisciplinary breadth, drawing from mathematics for elegant algorithms, cognitive science for understanding intelligence mechanisms, philosophy for grappling with reasoning and consciousness, and engineering for building systems that operate in unpredictable real-world environments. The multi-agent coordination revolution addresses one of AI's most challenging problems: determining who deserves recognition when AI teams achieve success together. This credit assignment problem becomes particularly complex when agents must coordinate at different levels depending on the situation. Sometimes individual agents make independent decisions, sometimes pairs coordinate for specific objectives, and sometimes larger groups must work together strategically. Zhao and colleagues introduce multi-level advantage credit assignment, a groundbreaking approach that uses explicit counterfactual reasoning to determine individual agent contributions. Their attention-based frameworks identify optimal agent relationships dynamically, enabling applications in autonomous vehicle coordination, distributed manufacturing systems, and collaborative robotics where cooperation structures must adapt to changing circumstances. Language models are undergoing a revolutionary transformation from simple text processors to central intelligence hubs that coordinate entire AI systems. Li and colleagues propose a paradigm shift in remote sensing interpretation, moving away from vision-centered approaches toward language-centered systems that integrate multiple reasoning modalities. Drawing inspiration from global workspace theory and cognitive science, their framework treats language models as cognitive central hubs that coordinate perceptual, task, knowledge, and action spaces simultaneously. This approach enables AI systems to understand satellite imagery not just through visual pattern recognition, but through sophisticated contextual reasoning that considers environmental factors, regulatory constraints, economic implications, and historical trends. The result is enhanced understanding that mirrors how human experts analyze complex geospatial information. Natural language data exploration represents a crucial breakthrough in making sophisticated AI systems accessible to broader audiences. Traditional approaches to complex data visualization require extensive technical expertise, creating barriers for domain experts who need to analyze sophisticated datasets. Recent advances in semantic block representation for volumetric data navigation address this challenge by encoding 3-dimensional scientific data into meaningful semantic units that can be accessed through natural language queries. Users can now explore complex medical scans, atmospheric models, or geological surveys using intuitive commands like "Show me high-density regions" or "Focus on boundary transitions." Reinforcement learning algorithms guided by semantic similarity scores learn effective navigation policies that respond to natural language descriptions, democratizing access to sophisticated scientific datasets and bridging the gap between AI capabilities and user accessibility. The breakthrough discoveries emerging from current research reveal several key findings that are reshaping AI intelligence. Counterfactual reasoning enables dynamic cooperation structures in multi-agent systems, allowing AI teams to adapt their coordination strategies based on situational demands rather than fixed hierarchies. Language-centered approaches consistently outperform vision-only systems in complex interpretation tasks, demonstrating the power of integrated reasoning over specialized processing. Semantic block representation makes high-dimensional data intuitive for non-expert users, removing technical barriers to advanced AI capabilities. Attention mechanisms, originally developed for natural language processing, successfully transfer across diverse AI domains, highlighting the increasing interconnectedness of AI research areas. Perhaps most significantly, these findings demonstrate that integration of different AI techniques produces capabilities that exceed the sum of individual component optimizations, pointing toward more holistic approaches to AI system design. The state-of-the-art research methodologies driving these advances represent sophisticated approaches to AI system development. Counterfactual reasoning for credit assignment involves training systems to consider hypothetical scenarios, asking what would have happened if Agent X had acted differently, to determine appropriate credit distribution. This approach handles complex scenarios where optimal coordination levels vary situationally, though it requires significant computational resources to evaluate relevant counterfactual scenarios. Language models serving as cognitive integration hubs treat these systems as central reasoning engines that integrate information from multiple sources and modalities, leveraging sophisticated reasoning capabilities developed through training on vast human text corpora. Semantic block encoding breaks complex data structures into meaningful units for independent processing, making high-dimensional data more tractable for both computational analysis and human understanding. Zhao and colleagues' work on multi-level advantage credit assignment addresses one of the most challenging problems in multi-agent artificial intelligence: determining appropriate credit distribution when multiple agents collaborate toward shared goals. Their research objective focuses on scenarios where agents may cooperate at different levels depending on task demands, formalizing the concept of credit assignment level as the number of agents that must coordinate to obtain particular rewards. The methodological approach centers on explicit counterfactual reasoning to infer credits across distinct cooperation levels, integrating advantage functions that analyze individual actions, joint actions between agent pairs, and correlated actions among larger groups. Technical implementation relies on attention-based frameworks to identify correlated agent relationships, allowing systems to focus on relevant agent interactions rather than analyzing all possible behavioral combinations. Experimental validation in challenging StarCraft environments demonstrates significant performance improvements over existing methods, particularly in scenarios where optimal cooperation levels vary throughout tasks. Li and colleagues present a revolutionary paradigm shift in remote sensing interpretation, challenging the dominant vision-centered approach that has characterized the field for decades. Their comprehensive work establishes a unified framework for remote sensing interpretation, capable of handling complex multimodal reasoning, semantic abstraction, and interactive decision-making that current vision-centered models struggle with. The theoretical foundation draws from global workspace theory, proposing that large language models can serve as central coordination hubs, similar to human consciousness, integrating information across multiple specialized processing systems. Their methodological framework treats language models as cognitive central hubs that integrate perceptual space for visual processing, task space for understanding specific goals, knowledge space for domain expertise, and action space for generating decisions and recommendations. This approach enables sophisticated reasoning that integrates visual observations with regulatory knowledge, economic factors, and historical trends, transforming AI from narrow specialists to general integrators, capable of human-like contextual understanding. The natural language volumetric navigation research demonstrates the power of making complex three-dimensional scientific datasets accessible through intuitive interfaces. This work addresses the significant challenge of enabling researchers without extensive visualization expertise to explore sophisticated volumetric data common in medical imaging, atmospheric modeling, and geological analysis. The approach involves encoding volumetric data into semantic blocks that capture underlying structural relationships, then using natural language processing techniques to match user queries with appropriate viewpoints and features. Reinforcement learning algorithms guided by semantic similarity scores learn effective navigation policies that can respond to natural language descriptions of desired views or analytical focuses. Experimental validation shows that users can explore complex datasets using intuitive queries, significantly reducing the learning curve for accessing sophisticated scientific data. The implications extend beyond scientific visualization to any domain requiring complex data exploration by users with varying technical expertise levels. Future research horizons reveal several key directions that will shape the next generation of AI systems. Scaling multi-agent coordination to larger and more complex scenarios represents a critical challenge, as real-world applications often involve hundreds or thousands of agents coordinating across multiple timescales and objectives. Future research must develop more efficient algorithms and architectures that maintain sophisticated reasoning capabilities while handling this scale. Improving integration between language models and specialized AI components requires developing better interfaces and communication protocols that enable seamless coordination while preserving interpretability and flexibility. Handling uncertainty and ambiguity in multimodal systems becomes crucial as real-world applications involve incomplete information, conflicting evidence, and uncertain outcomes. Developing hefted human-AI collaboration frameworks shifts focus from full automation to collaborative intelligence, requiring systems that understand human intentions, communicating reasoning processes clearly, and adapt based on human feedback. Creating sophisticated evaluation methodologies for these complex systems challenges traditional accuracy-focused metrics, demanding new approaches that assess multiple objectives, complex reasoning, and collaborative effectiveness. This AI synthesis and review was created using advanced AI systems to ensure comprehensive coverage and accuracy. The content synthesis utilized GPT Anthropic Claude-Sonnet-4-2025051 for analyzing and integrating research findings from multiple papers. Text-to-speech synthesis is powered by Deepgram technology to deliver clear, natural narration optimized for podcast consumption. Image generation utilizes Google's advanced systems to create relevant visual content supporting the research discussion. All content has been reviewed by human experts for technical accuracy and clarity, though potential oversights are acknowledged given the complexity and breadth of the research covered. Complete references and source materials are provided to enable further exploration of the topics discussed, ensuring transparency and enabling verification of the analysis presented. Subscribe to our YouTube channel to stay connected with AI frontiers and never miss the latest insights from cutting-edge artificial intelligence research. We provide weekly deep dives into breakthrough papers and methodologies, offering expert analysis that makes complex research accessible to developers, researchers, and tech enthusiasts alike. Join our growing community of AI professionals and enthusiasts who rely on AI frontiers to stay informed about the rapidly evolving landscape of artificial intelligence. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.